Dr. Panya Sae-Lim, he graduated from the Faculty of Fisheries University with the first class of honor and was ranked to 82nd Louisiana. He decided to continue for the high education award. In 2005, he was awarded the prestigious King Scholarship or Anand Mahindra Foundation from the King of Thailand. In 2006, he started to master program in animal breeding and genetics at Virginia University in Netherlands. In 2008, he graduated for the master degree and he continued for the PhD, which was the collaboration between Prida, USA, and Animal Breeding and Genomic Center. In 2011, he graduated the PhD and decided to do the postdoctoral research for 6 years in Netherlands for get more experience about his work. After that, I'm coming. Okay, sorry. Okay.
Thank you. First of all, I would like to thank the organizing committee for inviting me to give a talk today. My talk today actually about the application of NGS in selective breeding in aquaculture. So my class today is just to make you understand about selective breeding by 15 minutes. So it's really challenging for me and I will try my best. And if you have any questions, just stop me during my talk either so I can answer you there. I change the microphone. Okay, that one's better. Yes, much better. Okay, see to me. Alright. First, I would like to start talking about selective breeding. What exactly the selective breeding? It's just to select the domesticated animal to be as a parents based on your desirable trait or economically important trait. The selection criteria usually based on the natural difference on the trait, and that difference you can actually observe, you can call it phenotype. So each animal, they have different phenotype, and the phenotype, they are quite different. So basically, if you're looking at this animal or the fish, looking at the line, at the horizontal line, you can say that this is the generation of the animals. So if you perform selections, so say that you give the probability of some animal to be the parents for the next generation based on their performance or high performance, you basically improve the animal by, on average, of the animal in the next generation is higher than previous generations. And the difference between the average of the population is the genetic gain. So if you keep doing, the average of the population will increase. And alternatively, if you prefer the market size of the animal, so you can shorten the rearing period of the animal. So that is alternative way of using the selective breeding. If you don't do any selective breeding, passing by 5 generations, you still have the same average of populations. So this is much more efficient to have selective breeding in aquaculture. Selective breeding is the only approach that is generate cumulative and permanent increase in productivity in aquaculture. The importance of selective breeding, mainly to food security. Of course, aquaculture already contributes a lot to food security today, but selective breeding can make aquaculture to produce even more food. So, for example, if you're looking at this graph, 30 years ago, aquaculture for Atlantic salmon, it takes about 20 to 22 months in the seawater or sea cages to be able to achieve the production 4 kilo on average. Today, Atlantic salmon, they use a lot of selective breeding, and it reduces significantly the rearing period at the sea to about 13 months, or let's say by 1 year. They can get about 4 kilo on average. And this reduces a lot to the feed, the use of the feed, by half of the million ton per year. And that's value about 5 billion krona per year. I mean 5 billion Norwegian krona in that year. If the selective breeding continues to happen, the reduction in feed also still going on. I'd like to also start with the selective breeding a little bit more in detail. So what exactly determines the phenotype? Basically, we all know about the very basic genetic models. The phenotype determined by 2 key components, which is genetic and environment. So we can observe the phenotype, but we have no idea about genotype. We cannot see the genotype of the individuals. We see only the phenotype. So if we want to understand the mechanism or the pathway of genotype to phenotype, we need to do molecular biology, molecular genetics, for example. But if we don't do that, this is what we call a black box. So we don't have any information about this pathway. We use the phenotype, which is observable, to predict the genetic effects of the animal. And this prediction, usually we try to predict what we call estimated breeding value, or the EDV. We select on the EDV, and the question you might already have is that, does it really work because we don't know any pathway about genotype and the phenotype? Is the prediction is good enough to be able to ensure that you somehow get a good genetic gain? The evidence of genetic progress already published for several years. This is for aquaculture. Of course, in livestock, you already have many documentations. The genetic gain per generation is varied among different species and also different populations and also different traits. But at least you can see that even with this prediction of estimated breeding value, it really works quite well. So the genetic gain varies from 7% to close to 20% per generation, which is really, really high. But unfortunately, it's not the same story for overall survival and disease resistance. Some of the disease resistance genetic gain is quite high, but for example, the WSV, the genetic gain is quite low per generation. And the reason is the heritability is very low for this strain. The heritability explains the relationship between the phenotype and the genotype of the animal. So when the heritability is very low, it means that you can make a very slow progress, or your predictions accuracy is rather low per se. Now we see the limitation of prediction accuracies. So for some trade, you need to improve the accuracy to be able to get a better estimate of the breeding value, and then you can perform better selections. So especially for low heritable trade, and sometimes the animal must be in the disease-free environments. Something like the parents of the animal must be in the system that you need to make sure that there is no any specific pathogen. So most of the time you don't measure the trait or the phenotypes on the parents, but you measure on the close relative. And that actually also made lower accuracy of prediction of the parents, depending on the relationship between the relative and the parents. So I will give you more detail later about this point. And if you need to measure the trait that is quite costly, this is also problematic at the moment for the breeding program, and all slow down the response to selections. So how next generation sequencing actually help us to improve the prediction accuracies. There are two very important things that we combine together to make genomic selection possible. First, the next generation sequencing based localizing platform, and the methodology of the used genome-wide predictions, together we can do genomic selections. I will a little bit go to really overview of the genotyping platform first. In aquaculture, for the selective breeding, we mostly have two ways of doing it. Either the SNP array or next generation sequencing-based genotyping. The latter is referred to genotyping by sequencing. Maybe you might have heard about these technologies. Some people say that genotype or GPS, genotype by sequencing, is not the same technology to RADSEC. But in this case, let's consider they are the same at the moment. The RADSEC is the way to actually get a very high density of the SNP markers. Compared to the SNP array, you can also get that. But the comparison between these two technologies already published recently. And you can see that if you perform, you get the genotyping from RADSEC, the complexity of this method is quite high, because you need to have bioinformatician to do the analysis for you. Whereas you can get the genotype data directly from the SNP array. And the price is also quite relatively higher for the SNP array compared to the RADSEC. So people still prefer the RADSEC due to the cost of genotyping, but they sometimes struggling with the complexity of the analysis. So the RADSEC is restriction site associated DNA sequencing. It's a combination of genome complexity reduction by using the restriction enzyme together with the next generation sequencing technologies. This approach, we don't need to have any prior knowledge, for example, about the knowledge about the reference genome assembly. We don't need to have that, but it's good to have. There are different kinds of RADSEC, and it's already reviewed. So you can have a look on the bit later. The key implementation or application in aquaculture for RADSEC is the generating high throughput SNP markers used to make SNP array and constructing linkage map or QTR mappings or even genome-wide associated study, so that you can see the genetic architecture between the phenotype, different phenotypes, and also the focus of this talk will be about marker-assisted selection or MAS and genomic selections or the GS. So when we consider the genetic architectures, we mostly have two different architectures. So the variation of the phenotype is largely explained by just a few or major QTMs, or it can be polygenic architectures. I will start with the major QTL first. When the QTL is just a few QTLs mainly explain the variation of the phenotype, we prefer marker-assisted selections. A very clear example is the IPN virus in Atlantic salmon. It's already started, I think, even in 2008, before this paper. The IPN virus is double-stranded RNA virus, and the mortality during the outbreaks could vary from 0 to 100%. So it means that all the fish die. You totally lost the production. So if you're looking at the association between the markers and the phenotype, looking at the graph on the left-hand side, you see the different distribution between just a single marker, the Q, the big Q and the small Q. You see distribution of the big Q. The distribution is mostly in a very low mortality rate during the outbreaks. So the green color in this area. And this is the mortality rate, vary from 0 to 5, and it's 50, 20, 30 to 25, etc. to this interval. So the Q or technical Q corresponding to resistant to the IgMs. Whereas the small Q, clearly that the distribution is much broader and more covered to very high mortality of the IgM virus. So the heterozygous is in between these two distributions. And later that actually the study using the rat sequencing data to also pinpoint the position of these markers again, or this QTL again. They found the position of 21 centimorgan on chromosome 28 that corresponding or associated with the IPN QTL. And it's really quite strong peaks. So you can say that just one marker explains quite a large proportion of the variation of the phenotypes. So today, IPM is not that problematic anymore. They can easily improve resistance to IPM by just a few generations. So by selecting this capital Q and Q or heterozygous small q and big Q, you already reduce the mortality of IPM. I think it's really clear here. So compared to if you don't do selection. If the genetic architecture for the animal is polygenic, genomic selection is the method. I can see that it's now 15 minutes, so I have to speed up. For the genomic selection, you assume that there are many QTLs, not just one, affecting the variation of the phenotypes. And you have to assume that those QTL is in LD, at least with one of the markers. In fish breedings, what you want to do is that, and this is the most important, you want to actually make sure that the within family breeding strategy they are not the same, because otherwise you end up selecting the whole family and it's not that accurate. The way to do that is, you consider this. Suppose that you have two families, this family and this family. They are in the environment with disease free, and it's impossible to phenotype them because they must be. If you consider the animal from the same family, they must have the genetic similarity between them. And based on the pedigree information, they have a similarity, a half of that or 0.5 in terms of genomic similarities. So if you challenge the animal, you can use the information from the animal to estimate breeding value, and with the similarity of a half, within family animal, they get the same breeding value, plus 5, 5, 5, and 1, 1. So you end up selecting the whole family. But in reality, the few siblings, they share not a half similarity of the genome, but about 30 to 70% of the genome instead. So in reality, the genomic breeding value should not be the same of the for the animal within the same families. So this is the way of genomic selection. So if you have the genomic information, you can use to construct the prediction equation to estimate genomic breeding values and use to predict the selection candidate without phenotyping. And in this way, you increase accuracy. And the accuracy that can be increased is by, you can see that 20% to 41%, for example, Atlantic salmon in marine towers. They now go to full genomic breeding program, which means that they no longer use pedigree information. I think I'm getting to the final slide. This is my own study. I estimate the breeding value for the uniformity of growth in Atlantic salmon and using the pedigree relationship of single-step genomic variation, which means that I combine the genomic information with the pedigrees. If you're looking at the distribution of the breeding value, this is based on the pedigree information, and this is based on the 30 case mix markers. You can see that the distribution of the GEBV within family is much more different compared to this pedigree-based breeding value. And it provides also a higher predictive ability, up to 19%, for example, this trait, and 69.5% for this trait. If this is the truncation point for selections, you actually have much more contribution from different families compared to this one. So to conclude this talk, the next generation sequencing-based genotype has already helped us a lot to implement genomic selections and also enable us to get really high quality and dense genome-wide SNP markers. And also we can make a higher accuracy for genomic prediction and let us make more efficient food production. Thank you.